Alright, so these are going to be our next notes. These are on thermodynamics, and really we're going to look at two laws, the first law of thermodynamics and the second law of thermodynamics. Now this one really comes down to one word, and that's conservation. And we've seen a law like this before. If you remember from chemistry or physical science, we had the idea of conservation of mass, that when you have a chemical reaction that occurs, you have these chemicals on one side, they react and produce new chemicals on the other side, but the mass you begin with is the mass you end up with. Well, this is kind of the same thing. We have these situations where energy is being transferred. That's what heat is, transfer from hot to cold. Well, this is saying that when that process happens, when energy is exchanged from one thing to another, that it is conserved, it is not lost. And that also, you can see here, includes internal energy as well, like all the kinetic and potential energy of each molecule within the substance. So conservation means not lost, right? Okay, now it's important to remember that, still have to relearn how to do this writing stuff. So it's important to remember, though, that even though it's not lost, it may in the end end up kind of lost. I don't know if this is the greatest word. It's kind of used up through the, not used up, let's say it's kind of transferred to a place where you can't get it really back. So it's still there, but it's just not usable anymore. And that, two of the biggest culprits of that are friction and heat. So heat, as we know, hot to cold, okay, and sometimes that energy gets transferred to the environment and then it's not usable by the system anymore. And also friction, you know, when two substances touch each other, it gives off energy that way. Also lost, kind of same thing to heat, but that energy is then not usable anymore. And this is kind of this first law. It says, you know, energy is conserved in any kind of energy exchange. So if we continue here, I guess we'll leave it here for now. And the equation for this is the change in internal energy is equal to the heat, energy transferred as heat, minus the energy transferred as work. Okay, and we kind of looked at steam engines and the internal combustion engine, and we kind of discussed how we can use this idea of this transfer of energy as heat and use it to complete work. So, and really if you look at this equation, it really means that you're going to have something occurring with the internal energy, the particles within the substance. And the two things that are going to affect that are the heat, or the energy transferred due to heat, and the amount of work done. Okay, and this internal energy can go up or go down. It really depends on the situation that is occurring. So now we're going to erase this. Too many notes so far to add to it. But so the things we want to remember, though, is that we can have positive and negative changes. So as a result, that heat can be an increase in temperature and a decrease in temperature. So you can, this heat can result in a loss of temperature, or a gain in temperature, or a loss of temperature. And really we think about, if you remember what we did with those flasks, we had those little things, put the balloon on it, right? Okay, put it on a hot plate, we heated it up, and when we had this hot plate here and heated this up, the balloon expanded, right, because it just made the particles move at a faster rate, affected the pressure, and then this balloon blew up, right? And that is a gain in temperature. So if we were to, before we did all this, before we put on the hot plate, if we were going to take the temperature or the average kinetic energy of these particles, it would be a certain temperature. But after we did this, if we took the temperature again, we just can look at it and see, because it begins to boil and change a phase, that the temperature goes up. And that temperature causes this pressure change. And then think about what's going on here. So these particles are pushing out, right? this balloon, it gets bigger and bigger, and some of you got so big that you blew them up, and that's fine. It's a real good thing to remember what's happening. But then these particles get worked on, they get moved, they get spread out, and so that's positive work. So that's one example. The other example we did was, let me erase these annotations, was the other, when we went the other way. So we had the flask, and we already had the balloon blown up, right? And then we put it in an ice bath, some ice around it, okay? And then we should notice what happened is this balloon collapsed on itself and seemed to lose its air. And really what happens is the pressure difference on the outside, because these particles are then, the temperature is decreased. So if we were to take the temperature before we start, it'd be a certain temperature. But we know this is ice here, right? This ice-water mixture. These particles, the average kinetic energy, the temperature, these go down, and then that causes this pressure change, and heat is then lost, right? Because the energy in these then goes out to the ice, melts it, and starts to cause a phase change into a liquid. And then think about what happens here. Then these particles on the outside have a greater pressure, and then they do work on this system. So before we had the system where we were heating things, we were heating this flask, and that system of the flask and the balloon and the particles inside it, they increased in temperature, and then they did work on the surrounding environment. Here it's the opposite. They lose energy, their temperature decreases, and then the surrounding environment does work on them. Okay? In either one of these, work can be positive done by the system or negative done on the system. Both can increase or decrease the average internal energy, which is just, the energy of these particles. How fast are they moving? Okay, now, and also when we're thinking about this, we want to remember there's some special cases. So let's clear this off. Let's go down here and we'll be almost done. These notes aren't too long. And we have these things called isovolumetric, isothermal, and adiabatic. And there's really three conditions here. And you look at this term iso, and iso here. And what this iso means is the same. So it's iso, the same volume. So these are conditions where there's no change in volume. And an example of that, they have these little chambers, and really the little, when we did this specific heat capacity, we had those little containers, right? Okay, and we had a hole in here. We put the thermometer through it, and then we had some water in here. Okay, and we then heated up this water, changed the internal energy, and then we could figure out by that change in the transfer of energy what that material was or whatever. But think about this container. When we add this energy to it, it may change the temperature of this system, but it doesn't change the volume. And that's called an isovolumetric system. Okay, and then it can also be an isothermal system. And this means no change in temperature. A really good example of this is a phase change. So if I was going to erase this here, and we did a lab where we checked our thermometers, right? And we took a beaker, put it on a hot plate, heated it up, and we noticed we had this curve, right? Flat lines, goes up again, flat lines, goes up again. And we know where this is a change in temperature. This is the solid, this is the liquid phase, and then this is the gas. And we had this stuff called latent, or this idea called latent heat. And latent heat is this transfer of energy where the temperature doesn't change. And if you remember, when it's changing, from a solid to a liquid, where it's melting, okay, there's a time where it's part solid and part liquid. And depending on the substance, this time, this flat line where the temperature doesn't change, can be really long or very short. Okay. But there's no change in temperature. If we were to take the temperature here where it's changing, this melting point, we would probably find that this temperature, if it was water, was right around that melting point. So 0 degrees Celsius. It kind of stays 0, 0 all through here, all through here. Then all of a sudden it goes up again. And if we looked at the substance, if it was water, we would see all the ice is gone. And we can kind of gauge what is happening in the phase by noting these. It's changing temperature, then it doesn't change temperature. That's a phase change. Then it starts changing temperature, and we know it's completely, all the latent energy or heat has been used up, and then it starts rising again, and we know again that liquid's then going to change to a gas, and it's going to flatline again. We call this process where the temperature doesn't change an isothermal process. The last one, let me erase this one. The last one is adiabatic. And this is where there's no transfer of heat. These, again, aren't all that common, but an example would be if you blew up this balloon. Now what you would see if you, put some air into here, maybe you used a pump instead of blowing it up yourself. So use a little pump here, make it on something like this. If you're blowing this up by, just using your own breath, it takes quite a lot of energy to use that. And again, there's going to be friction and all kinds of things like that. So then the temperature, you might be able to notice the temperature changing. When you use something like a pump, this air just comes instantly in here, and you're going to see this change in volume, right? And you're going to do some work because this balloon is expanding, so you're going to do some work on the environment around it. But the temperature really won't change, and we call that, or there's no change in temperature, so there's really no difference in temperature, so there's going to be no transfer in heat, and we call that an adiabatic process. And that's kind of the special cases. Most times you're going to see changes in all these, but sometimes there's not, and we have special names for those. And so if we go back here, we want to remember our equation. The change in internal energy, this is the the particles inside there. So if we had, like we had our flask, we have some water in here, and all this water is made up of particles, right? And they're moving around, going this direction. They're spinning. They also are attracted to each other. Liquids are still subject to intermolecular forces, so there's energy in that as well. So that's what the internal energy is talking about. And then if we do something to this, this can then exchange, and increase its temperature, decrease its temperature, whatever. It can then interact with the environment and transfer some of that heat. And a lot of times when that happens, it causes work to occur. And that's kind of, we can use this equation. If we know two of them, we can solve another one. So how much work does it do? If we know it, usually it's not going to be this internal energy. Usually it's going to, how much did the temperature change and how much work did we do? And that's going to be usually solving for this. And if the change in internal energy, it's going to have to probably be given to us. So keep that in mind. In this first law, conservation of energy, energy cannot be created or destroyed, just transferred from one type to another. And that's kind of the notes. Let me know if you have any questions, and fill these in, annotate them, and turn them into the box.